our a PPT showing our departmental profile. Just have a look at it to get some idea about department or institute as a whole. From the beginning, please. Okay, thank you, Dr. Farooq Mondal. So I think it is right time to start. Without any further delay, I think it's better to start. So, Professor Mondal.
Yes. Hello.
Yes, sir. Am I audible?
Yes. Start.
Okay, sir. My greetings to one and all. I welcome everyone to the third lecture of the ongoing webinar series organized by the Indian Institute of Metals Students Chapter, NIT Durgapur, in association with the Department of Metallurgical and Materials Engineering. Before moving ahead, I urge the attendees to kindly mute their microphones and switch off their cameras for smooth running of the event. As you know, learning never stops, so does discovering. All that matters is an individual's endeavor to take up challenges and face them. Keeping in with this view, the newly inducted Students Chapter of IIM NIT Durgapur is enthralled to have begun its journey, striking the right chords with the series of webinars. And we are pleased to have Dr. Dierk Raabe encouraging us today in our effort. Without any further ado, I request Dr. Madan Mohan Ghosh, HOD of Metallurgical and Materials Engineering Department, to speak a few words about the prospects of the activities organized by our department to our guest. Please, sir.
Okay, thank you. Respected speaker and dear participants, a warm and hearty welcome to this online interaction session. Today we are glad to have Professor Dierk Raabe of Max-Planck-Institut, Germany, as a speaker in this online lecture program. This program is being organized by our department in association with Indian Institute of Metals Students Chapter at NIT Durgapur. I would thank our institute authorities and all functionaries of IIM Kolkata for extending their support to organize this program. And special thanks to the coordinator, my colleague, Dr. Farooq Mondal, for his constant effort to organize such kind of a program. This kind of function will enlighten our department, will enhance our department and our institute as a whole. For the progress of any engineering department or institute, there should be some interaction, some suitable platform of interaction with other academic institutes, research organizations and industries. The Department of Metallurgical and Materials Engineering of National Institute of Technology Durgapur is really privileged today to interact with Professor Raabe, to hear from him, and who is a very great personality in the field of computational design of materials. On behalf of the whole department and whole NIT Durgapur, and on my personal behalf, I express a warm and hearty welcome to Professor Raabe in this online interaction session. Our department has organized several courses, seminars, etc. during the last 2 years, and during this COVID situation, we have nothing else to do rather than to organize this virtual kind of programs in virtual platform. So we are organizing now the webinars, and this we are organizing almost on a regular basis. And today's webinar is the third in the series, as mentioned by Robin. And in this series of webinars, we have several others. We have one more. We are organizing and in this webinar series, we are organizing online lectures by renowned professors, researchers from leading foreign universities. I request all the participants of today's program to attend the subsequent webinars as well. I can see a good response from the participants on today's program. I hope the webinar will be extremely beneficial to the participants, and participants will surely gain some know-how in this area. And we are thankful to Professor Raabe for being with us as a speaker in this webinar instead of his very busy schedule. And I am sure this platform, this interaction program will be a good platform for the initiation of research collaboration and network formation between our department and Professor Raabe and his group. I hope all the participants will enjoy this program, and I wish all the success of this program. Thank you all. Thank you.
Thank you so much, sir, for your sparkling words and being tender towards us. We now move on to our today's technical session. We are extremely glad and grateful to have Professor Dierk Raabe grace the occasion with his presence. The topic of his talk today is multi-scale and multi-physics simulations of chemico-mechanical crystal plasticity problem for complex engineering materials using DAMASK. Dr. Dierk Raabe is a professor in the Max-Planck-Institut at Germany. He studied physical metallurgy, metal science, and music from RWTH. Dr. Raabe works in the field of material simulation, atom probe topography, microstructures, and resulting mechanical properties of metallic alloys. He wrote and edited several books on this topic like computational material science, continuum scale simulation of engineering materials, and crystal plasticity (FEM) in material science and engineering, as well as more than 600 peer-reviewed publications. He conducts detailed comparison between simulation and experiments. He is currently working on the issues such as local thermodynamic phase states at confined spaces, such as at lattice defects, alloy designing, high entropy alloys, atom probe tomography, and the further development of in-the-house simulation toolbox DAMASK on crystal mechanics, multiphysics, and property prediction of complex materials. Professor Raabe is a frequent plenary and keynote speaker. In 2004, he received the highest German research award, Leibniz Award. In 2008, he was awarded Li Hsin Lecture Award of Chinese Academy of Science, and in 2011, the Lecture Award of the University of British Columbia. In 2012, he received an ERC Advanced Grant, which is the largest single researcher grant in Europe. Dr. Raabe mentored more than 55 PhD students. Since 2010, he is a member of the German Council of Science and Humanities. He is a professor at the RWTH University, member of the National Academy of Leopoldina, and honorary professor at Catholic University in Leuven in Belgium. Since 2012, he is the chairman of the Governors Board of RWTH University. He is a member of the National Academy of Leopoldina. It's impossible to describe his research experience and his devotion towards our society and to the upliftment of the society. So without any further delay, I would like to invite our honorable guest speaker, Dr. Raabe, to share his knowledge with us on the selected topic. Please, sir.
Yeah, hello. Thank you very much for the very kind. Can you all hear me and see my slide?
Yes.
Very good.
Clear. Both are clear.
Very good. So, yeah, thank you very much. I'm very honored and thrilled to be with you here again. It's a very kind invitation, and I hope I can convey some of my excitement about our field with you. Maybe I first would like to share some slides with you about my institute. So the Max-Planck-Institut in Düsseldorf has currently 4 departments. There's one on computation materials design from my colleague Professor Neugebauer, mainly on density functional theory. And we have one about micro-nano mechanics from Professor Dehm. My own department is on microstructure physics and alloy design. I'll show you later more, of course. Then we have a department on surface science and chemistry from Professor Stratmann and an independent group on nanoanalytics from Professor Scheu. So we are about 350 persons on board and have a budget of roughly 23 to 24 million per year. That depends on the third-party income. So the institute is more than 100 years old, and with that we are one of the oldest existing institutes of the Max Planck Society. And our mission statement is shown here. We work on the basic science of complex engineering materials under real environmental conditions down to electronic and atomic scales if we have to. So we organize the work in our institute across a couple of more global focused topics. So we develop really new materials. Here's just an alloy that swims in water. It's a magnesium-lithium alloy. In computation material science, machine learning, we have many activities. Here's just a little glimpse of a biomedical alloy, with low elastic stiffness that we developed a few years ago. The Institute is very strong in the field of characterization, down to the atomic and electronic scales again. This is just an example of a recently published work from my colleagues' department on phase transformations in grain boundaries. A very important topic is research on hydrogen-related problems and corrosion, of course. And here you see just a little picture about the measurement of deuterium on an iron surface. So we really try to get to the fundamentals of hydrogen. And recently we have a rapidly growing field where we work on the sustainability of material science and metallurgical processes. But let me get to the main core topic of my presentation today. As was already kindly announced, the topic is about using DAMASK, which is our in-house developed code for solving multi-physics problems in the field of crystal plasticity and transformation. And you see the authors, the co-authors with whom I have developed this package over more than 25 years now. And special thanks, of course, go to Professor Tazan, who is now at MIT, who was with me for a few years, and I will highlight his work as we go along, and other colleagues who work on advanced BSD techniques. So we all know why this topic is of interest at all. We know that we produce about 2 billion tons of metallurgical products about every year. And we all know that this goes along with a huge global energy demand of 8% pertaining to metallurgical products. And we are also causing by that about 30% of all industrial greenhouse gas emissions. On the positive side, we of course have a gigantic market related to materials, specifically to metallic materials. And we talk here about a quantity of 3,000 billion euros turnover every year, where the majority relates to metallic products. And we know that the properties of our alloys are typically requested at a macroscopic scale, be it mechanical properties and corrosion. But we need to understand the defects, of course, at the atomic scales. And that interplay of defects, properties under certain boundary conditions and processing is what we are interested in today, particularly related to the question of how we can cast this into a digital twin. So the question is how we can put this understanding into mean field constitutive formulations that we can subject to a boundary condition and initial value treatment so as to make it accessible to advanced simulation methods. And today I will show you particularly how we use such crystal mechanical and constitutive simulations in the field of advanced processing simulation, of advanced forming, and microtexture evolution predictions. So it's a triviality that mass and energy are conserved quantities, but microstructure and properties are not conserved, and they are also not in equilibrium. They are maybe in local mechanical equilibrium, of course, but there's no steady state equilibrium throughout the material. And all these features have to be properly considered in any mean field constitutive formulation that we use under the framework of the DAMASK package. That means the simulations must be microstructure sensitive. And we all know that the properties of the materials are, particularly the mechanical properties, are designed through the microstructure, and the microstructure is amended through the processing of the material. And hence, again, the main message that I want to share with you today is how we realize it to make such formulations mechanism and microstructure sensitive. Let me show you just a little appetizer, a little example here related to the field of aluminum alloys. On the left-hand side, you see the tensile strength plotted against the alloy families. So you're all aware of these many alloy families that we use in the field of aluminum, from packaging towards automotive engineering, aerospace engineering, mobile communication, and so on. And I also plotted here additionally kind of the main alloying elements that are exploited in these respective alloy families. And we see that there's a substantial influence, of course, of the composition, typically turned into nanoprecipitates in such aluminum alloys. And we, however, can also appreciate that when you look at the corresponding scatter bars pertaining to each individual alloy family, here shown exemplary for the 7075 alloy family, so ultra high strength 7,000 alloys, that you have a huge range of properties, here the tensile strength, that can be influenced by the microstructure and by the processing. That means that is a take-home message from any such simulation, that we have to alter and adjust and understand and simulate microstructures to serve that specific need, exploiting the variability of properties in terms of the underlying microstructure. Now, what is meant by microstructure? That is, of course, a triviality to metallurgical experts, but we start at the single crystal level with point defects, and when we widen our view, we can appreciate that we have more extended defects like interfaces, grain boundary, phase boundaries, dislocation arrays. You have textures, crystallographic orientation distribution functions, cracks, phases, precipitates, and so on. So we all know this really complex interplay of microstructures, and as said before, the direction in which they want to evolve is, of course, determined by the thermodynamic potentials, but they are largely affected by the processing, the rising metastability. And we want to understand that material not only out of the microstructure, but also under the influence of the environment, here shown in terms of some diffusing gas atoms like hydrogen or oxygen. That means we have a real hierarchical data, and we have its associated chemistry, and that's where the classical microstructure research goes system dependent. So let me start more specifically now with an example of dual phase steels. So this is very well known in the field of automotive applications, for instance. Here you see the classical DP microstructure consisting of ferrite grains and martensitic regions. And these materials are highly appreciated, and used particularly for highly stressed parts in automotive design, for instance. They have a high ultimate tensile strength, UTS, low yield strength, which is good for forming operations, but they have sufficient ductility, good formability, no Lüder strain, that is very important for engineering parts, and they have highly tunable properties and, of course, very, very low costs. Now, the tuning comes, for instance, through measures like grain size reduction or martensite volume fraction increase or carbon content increase. And we all know that would come also at the cost of ductility. Let me zoom into such a martensitic region. You can, by EBSD, measure the former austenite grain from which the martensite was formed, and you can reconstruct the different packages of the martensite. And when you switch, for instance, here like to the electron channeling contrast imaging mode, you can also reveal the lath substructure, which is very heterogeneous, and you can do that even in 3D when using serial section. I'll show you later more about it. And in TEM, you see now the very fine lath that are in part as fine as a carbon nanotube, and you see overlaid here by an atom probe measurement the positions of the carbon atoms, which even in martensite we know the carbon is not fully quenched in, as we write in textbooks, but the carbon can always during quenching do a couple of atomic jumps, decorating, for instance, the internal interfaces, such as, for example, the lath interfaces or the dislocations and so on. So you even have classical iron carbon martensite in such a DP steel a slightly higher than expected carbon content that is decorating the defects. Now we subject such microstructure ingredients as martensite to in situ tensile tests. That was a nice activity that was built up by Jem Tashan at our institute over the past years. You see then can study, for instance, the mismatch, the elastoplastic mismatch between adjacent fine and coarse lath. Let me jump back from the atomic scale or microstructure scale into the macroscopic engineering scale. Here you see now a very engineering test where you see the two flow curves, one for DP800, so a dual phase steel with 800 UTS, and a TWIP steel. TWIP stands for twinning induced plasticity. And you see the two vastly different stress strain curves. And we typically would assume that for a crash relevant forming part, for instance, the TWIP steel should behave quite good because you have a huge integral over stress and strain, which states that a part that is made from such a steel should have a very high energy absorption capability. Now you see here a typical crash experiment conducted on both of these materials with such a typical crash box. And interestingly, we can learn from this that the DP steel with the lower integral, so with a lower total mechanical work, performs actually much better than the TWIP steel with a much higher integral. So that is kind of a surprising result at first view. But when you look a little bit closer and you look at some of the strained points, particularly here from the highly strained parts and the buckling area of these crash boxes, and translate them back into these simple stress strain curves, then you can see that the maximum strain does not exceed like 18 or 20% maximum. And that means the high strength in this area means that only this part of the total integral is really needed for designing such a part. So the very high energy absorption capability of this TWIP steel as a counter example is actually not really needed for this specific design of such an automotive crash box as shown here. That is quite trivial for a mechanical engineer, but the message here is that the energy absorption depends, of course, not only on the specific alloy you use, but of course on the nature of the part and on the loading scenario. And that means you learn here also that any digital twin or a simulation method that brings together microstructure and mechanics must be tensorial in its response and account for the tensorial nature of the loading scenario, hence must include the texture and the orientation-dependent parts of the microstructure. So that is at the very core of this simulation package DAMASK, which you see highlighted here as a little teaser. And we developed that, as I said, now nearly 25 years and have many, many customers and colleagues around the world in industry and academia who use that. And we are just before a new release. So very soon a release of Webinar-3 will go public. And it includes a couple of features and capabilities that you can do with this simulation package that I share with you during the course of this presentation. Let me show you one workflow more starting at the microscopic level. So we have, for instance, like shown here, a scanning electron microscopy approach and microstructures. Again, we stay for a moment with dual phase steel. So you see again the fine ferrite grains and do this with an in-lens detector setup in the scanning electron microscope. Then you avoid this typical topography contrast that you otherwise get from such soft, hard contrast microstructures like DP steel. And then you get a much smoother surface appearance and your digital image correlation is not affected by surface topography. So DIC stands here for digital image correlation, which allows you to take the surface strains from such experiments. And we will later see that we have to appreciate that microstructures in such complex materials are, of course, three-dimensional in their topological nature, and that must be in part accounted for. And then you get the experimental strain maps, for instance. Now on the simulation side, where we try to mimic that with DAMASK, you first render your microstructures of interest digital. That can be typically done by different methods associated with pattern recognition, with machine learning, or simply using certain features from the EBSD results, like surface pattern quality. And then you have to retrieve, by here in this case, by indentation, for instance, the single crystal mechanical data that you need. But we have also macroscopic inversion methods from which you get the single crystal data that you need for DAMASK, because DAMASK needs the information from the slip system level because it's a crystal plasticity code. Then you can solve your system using either spectral fast Fourier codes or finite element codes and get the strain and stress. Let me jump back to a very trivial picture that we all know from textbooks, just as a reminder of the underlying mechanisms that we try to describe in crystal plasticity models. Here you see such a nice picture from a textbook with surface steps coming from the glide of dislocations. Of course, the surface steps are much bigger than one Burgers vector because we have, of course, a number of dislocations coming from the same source. And then you can use, like plotted here, the well-known Orowan equation, which allows you to calculate the shear rate gamma dot from the activity of these mobile dislocations, their Burgers vector, and their velocity field. So you have a very simple mean field access from Orowan theory, from Cox making extreme type of theories to translate populations of many dislocations into the corresponding kinematic measures that you need. When you want to describe the strain hardening, you have, of course, like in a Cox making model, have to account for the dislocation interaction, or you can consider here the mean free path reduction, like shown in this little animation or movie. When a grain boundary is in your way, then you can describe the reduction of the mean free dislocation path in a harmonic way, where you add up in a harmonic formulation all the obstacles that are in the path of a moving dislocation set, and that would contribute then to the strain hardening in a case of a Taylor formulation. What is really important for more complex steels are TRIP and TWIP effects. TRIP stands for transmission-induced plasticity, while TWIP describes twinning-induced plasticity. And you see here an in situ microscopy movie where you see how at the tip of the martensite you create rich populations of dislocations that are emitted because that martensite that is formed under mechanical loads is not commensurate, it's not compatible, and has a different volume than the adjacent austenite. And that creates a lot of misfit plasticity that hardens the material. Likewise, on the right-hand side, you can see here a typical in situ TEM image from a movie from a TWIP steel, where you see that the formation of twins produce a confinement of the plastic slip of the dislocations. And the hyperbolic function telling you that the stress for that half Frank Reed source operating here is scaling with the spacing of these twin walls. So these were just some examples where we try to translate elementary physical metallurgy mechanisms then into corresponding mean field formulations, mainly through the reduction of the mean free path or the stress you need to activate Frank Reed sources. Now a bit of the kinematics, because I told you all of this has to be written in dyadic form, in tensorial form, and not in scalar form. And here you see again a very simple textbook equation from my classes on micromechanics when we pick a body-centered cubic crystal structure and assume that you have 48 slip systems. You can, for each of those, calculate what you know typically as a Schmidt factor, which is, of course, again, a Schmidt matrix or Schmidt tensor. And you can calculate this into a two-dimensional section of the otherwise five-dimensional convex yield surface of a single crystal situation, and then plot these kinematic bounds where you activate certain slip systems as lines. So the lines, the red lines that you see here, the dotted lines indicate when your arbitrary stress tensor projected into this 2D slice here reaches the critical stress to activate a certain slip system. When you add to this the 12 112 111 systems, or even the 1 2 3 111 systems, where 111 is of course the Burgers vector divided by 2, and the first indices are the glide planes, then you get a more complex shape of your local dyadic response. And again, so all of these glide systems come of course with an individual strain hardening behavior that is described by these constitutive laws I described before. Here's a second simple animation from my class, which shows you a single crystal, similar as we saw it before from this textbook picture. And again, everybody knows that you have a certain Schmidt factor or Schmidt tensor, and you shear the material. But we learned from this very simple picture a couple of things. You see that the crystal is typically deformed under certain constraints. This sounds very trivial, but it cannot move freely as shown in this little animation, but it is tied to these holding grips here in the tensile machine, or it can be due to constraints by the environmental crystals. And that means you have only these geometrical constraints, these boundary conditions that enforce certain crystal rotations. And the fact that these boundary conditions are not homogeneously distributed across the expansion of such a crystal means that you can also have gradients of such crystal rotations from one surface to the other, which very easily explains why often the texture in micromechanical evolution is very heterogeneous even inside grains. So I found this view graph may be helpful because even such a simple kinematic point can be made readily clear on such an example. Now we have to translate always these crystal kinematical aspects into continuum space. And here you have our formal description of two coordinates, which are both shifted as indicated by these blue arrows by a displacement vector u1 and u2. In this case, the displacements that describe the distortion that you impose on this block, on this continuum, are identical. And when these 2 points represent that block of material, that means you are just shifting this continuum from left to the right. When you repeat that thought experiment, but you impose two displacement vectors here shown in blue, which are not identical, both either in magnitude and or direction, then you impose a distortion. That means these are not compatible. That again sounds trivial, but that's how you formulate the displacement gradient. That means only the lateral gradient of the displacement field is that what gives rise to be accommodated by dislocations or trip or a trip effect. That means the strain is just one possible linear, additive, or polar measure for the distortion that we typically use. The physics quantity that you need to match is the so-called displacement gradient tensor. And that is what you describe in terms of the individual dislocation fluxes in each of these directions. Because that mismatch that you see described here in classical continuum mechanics has crystals to be accommodated by the shear carriers like dislocations or trends. And in DAMASK, we represent all these anisotropy features now at the integration point, be it the elastic, the phase composition, the shear rates, the O1 equation I already told you, the Schmidt factors in a polar kinematic framework, the crystal orientations, and of course also possibilities to do local homogenization at a spot. When you describe a bigger engineering part, your point cannot describe a single crystal, but it must already describe an agglomerate, a mean field set of crystal orientations or phases that you homogenize and feed that information back to your integration point. And since recently, we also work on details of damage evolution, mainly with Pratik Chandrash, who is now at Manchester University, and with Bob Swenson, who is at RWTH in Aachen. Because maybe the biggest challenge that we currently encounter in such simulations is how to predict also the gradual evolution of microstructure-related damage in such materials with their high degree of inhomogeneity. So that gives you just a rough impression how the setting in DAMASK works, on which constitutive parameters have to be taken into account. That means you can retrieve the information that you need to map here, both either from microtexture measurements or from X-ray texture measurements, and subsequently decompose it. I'll show you here a 20 years old example on which we worked in the beginning. A high purity aluminum grain, you see in black the grain boundaries. So a very simple example with columnar grains, and that was deformed like shown in this little animation. That was deformed by a lubricated channel die experiment in order to achieve near plane strain boundary conditions, so to have well-defined mechanical constraints. And when you then measure the deformation of these, here this is the experiment shown in color code now, you see that just from the variation of the orientation, you get an enormous inhomogeneity of this deformation pattern. You see the little blue grain in the center was practically not deformed. When you even have 15% total thickness reduction of that polycrystal, columnar polycrystal, you see that some of the grains have undergone a deformation beyond 20% locally, while this very hard rotated Gauss grain in the center, this little blue grain, has deformed not more than 2 or 3%, while the entire sample was loaded 50%. So that shows you from a very trivial high purity aluminum sample how enormously inhomogeneous such a deformation can be. And that is just the 20-year-old simulation result that we achieved by finite element calculations, by crystal plasticity finite elements. This is another example that we did with Raul Radowitzki also like 15 years ago. And here we used a somewhat already more complex setup in full 3D with a crystal plasticity calculation, did very similar experiments again, and found very similar, very good agreement. So that's how we step by step developed these techniques. Now, let me show you a bit more in detail what we have been doing over the past 5 years on more complex steels. Again, going back to the DP steels with ferrite and martensite. And here you see such a calculation based on this microstructure I've just underlaid before. And you see just only for a simple tensile loading situation, the enormous variation in the local stress that you predict. So here in blue, you see a gigapascal range stresses at local mismatch features. But interestingly, you see even compressive stresses, which means that happens when two very hard areas are moving together by the constraints, and they can set local regions even under compressive load. So this is something that you get out of a more complex microstructural landscape, such as encountered in many complex steels. When you now, however, go stepwise through each of these volume areas and study in detail the quality of the agreement between experiment and simulation, like you see second and third row here, then you can see nicely that while some of the features, particularly around the hard martensite particles, agree quite well between simulation and experiment, other features deviate quite a bit. And so the reason for that is like here sketched with this little picture, is that of course the microstructures are in reality three-dimensional. And this in part affects the surface results of the strain and stress, of course, that you measure. So we have invested a lot of time and effort over the past 10 years to develop a 3D serial sectioning technology. So that was all built in-house with markers, set markers, and an automated serial sectioning technique, which works by combining a polishing machine, very classical polishing machine that is run completely by a robot. So there's no researcher involved anymore. And then as you see here, the robot takes the polished sample out of the polishing machine, and the robot charges that sample into the microscope. We connected the robot to a Gemini size microscope, so for high resolution field emission measurements of ECI contrast, of EBSD contrast, and so on. And you see how the robot is alone operating this and starting to do the measurements, getting you the microstructure results you want. Then the robot stops the experiment, takes the sample out, and runs the next polishing round. And you can, of course, define the thickness that you have removed between the subsequent serial sectioning polishing steps, and can get all kind of microstructure 3D information, such as a corrosion fraction as a function of corrosion time for different grain boundaries and so on, like here from a stainless steel. Or you get results like shown here from a copper sample that was subjected by an ECAP process. There was a project by Peter Koneinberg and Supu Chai and Stefan Zeffer, where you get not only the three-dimensional microstructure, but of course all the associated higher order kinematic information, such as the nature of the crystallography the grain boundaries, like showing here the population of the 60° 111 grain boundaries. You can differentiate between the tilt and twist boundaries. And you get data packages such as shown here, where you see both the grains. You also get, of course, the individual pattern qualities and so on for discrimination among phases and the associated interfaces. Now we do the same thing also here for steels. I've shown that movie already before, where you get such 3D data, for instance, now again for a dual phase steel. And here we ran now such a box of 3D data by DAMASK, and you see you get a real high fidelity simulation of the strain and stress distribution also from such 3D microstructures. Now we took a much bigger patch that was done in a big project by my colleague Martin Diel, who is also now a professor at University Leuven, just started a couple of months ago in Belgium. And you see we did the same thing. We render this microstructure digital, but you must appreciate this is now a three-dimensional microstructure, so consisting of many such slices, as I've shown you before, retrieved by this technique. And you see here now the corresponding computer simulation where this is uniaxially loaded. And you see the equivalent strain and equivalent stress distribution that arises. And when you compare that in detail step by step, like I've shown before, you get a much higher fidelity of the reproduction of your measurable surface strains due to the fact that you really account for the microstructure layers that you have also below the surface, which, however, of course, affect the surface stresses and strains. And this is not only important for getting a more plausible or more trustworthy result of your simulation, but it's for us very, very important by that to really test your methods and develop proper models for damage. As I told you, we also use this with jumping out to the other side of the scale end. We use this also for homogenized crystal mechanical simulation of larger forming parts, such as, for instance, done in projects in-house in collaboration with industry for automotive sheet forming, or for the development of advanced yield surface functions. Or we have recently written a couple of papers where we show how you can, on the fly, calculate yield surface parameters from crystal plasticity models. Now let me turn to a couple of pending points on which we currently work. I don't go into so much detail, but show you only briefly where we have currently construction sites. One is, of course, damage evolution in materials which have high mechanical contrast in the microstructure, like DP steels, or of course other materials too. And you have a couple of shown here feature patterns, such as martensite fracture, such as delamination between martensite and ferrite, and so on. And as you all know, this is maybe the biggest point in high-strength materials development, that you can predict the microstructural evolution of such damage features, both during manufacturing, during processing, and during use. There are two results that we did together with my colleague Pratik Chandraj, who is, as I told you, lecturer at Manchester in the UK. And you see here a couple of results of heterogeneous microstructures, where you see in the blue color the evolving topology of the cracking in this material. I don't go into much theory detail here, is not enough for doing so, but just for the experts among you, we do this in principle based on an extended Alan Kahn type of theory, where the idea is that you devise a Landau type potential functional form in which you, like in a classical Griffith form of classical fracture mechanics, introduce the balance of the elastic energy density, the plastic energy density, and the surface energy that you have to balance in a functional form to predict where a crack may evolve. We couple this also completely with thermodynamics and with Kalfat coupling, so that you in the software can also run phase field simulations, but with full appreciation of elasticity and plasticity, such as shown here for the time scale, which goes from left to right, where you see the plastic strain that evolves around the interfaces of this classical Oswald type phenomenon. So this is just, again, without going into much deeper, showing you that we also go on working on combining the crystal plasticity with, of course, anisotropic elasticity and with phase field and phase transformation problems and with fracture problems, because these things are often in modern materials, of course, closely entangled. Now, at the end, I would like to share a few thoughts with you about ongoing work, all unpublished, so on microstructure prediction at very fine scales. So here we have now different mesh refinement techniques that we currently test and play with. And I just want to show you some preliminary results. You have now 3 different microstructure pictures, all simulated. So this is not an experiment, this is all simulated. And you see when you go now to higher deformations and go from that coarse grid again and to a very fine mesh, that you see what level of detail you are capable of obtaining nowadays with such crystal plasticity calculations. When you just look at the bottom image, 75% thickness reduced IF steel, so it's relatively close to pure iron, then you see a quality of the calculation. This is a spectral calculation, fast Fourier solver with DAMASK, where you see a microstructure that looks very similar as what you typically know from EBSD and microscopy measurements. So we currently try with that to push really the limits also on the microstructure prediction side, which is, for instance, then important for recrystallization. And so with that, I gallop quickly now towards the end of the presentation. This is again just a little teaser about our DAMASK simulation package, which allows you to do many of these things. Some are still pending, not implemented, but some will soon come in the next version of DAMASK. And we cover not only the engineering scales like yield surface for forming operations, different types of yield surface packages, but of course inner damage evolution. And here the engineering part ranging from the 3D EBSD microstructure side up towards on-the-fly calculation of yield surfaces that you might need for predicting forming and shape operations for, example, for the automotive industry. And our mission is really that we make sure that these quantitative formulations are not empirical, but they are really based on the microstructure physics understanding. And with that, I stop here. I thank you again very, very much that I could speak here today in your seminar. And I leave that slide with some reading and was, of course, with some acknowledgements from our funding agencies. And with that, I'm happy to take some questions. Thank you very much.
Thank you, Professor Raabe, for your nice presentation. I think the participants, our students and research scholars all have enjoyed. It's a very nice. So now I request the participants to ask questions if you have.
Participants from MS team, they can raise your hand ups. And participants who are attending through our Facebook Live or YouTube Live channel, they can write their questions in chat box.
So, Professor Raabe, I have a question. Is this a freeware or is needs to be paid? It's licensed, open source or?
No, this is all. Thank you for the question. This is all open source software. So this is not commercial software. It's all totally free and can be downloaded and from our websites.
Okay.
Yeah. So we have DAMASK websites, and the new one is under preparation, the new version, and that is totally free. And it's also used by many national labs in the US or by many companies, and yeah. Okay. So it's without any costs attached. And we currently also work in parallel in many other projects, for instance, rendering this into something like a Jupyter notebook environment, then you can patch your workflow much better together and so on. Yeah.
Is this package entirely crystal plasticity model based, or some other model technique is incorporated, like APM? It's a combination of APM and crystal plasticity, that DAMASK package. What is that?
So for you have a wide variety of constitutive formulations that you can use, and you can couple it with different solvers. So on the constitutive side, you can do, of course, linear elasticity, anisotropic elasticity, all the standard things. You can do everything that is related to texture, crystal mechanics, phase transformation, and so on. So it's relatively broad in the constitutive laws that you can select and use. But it's generically more in the direction of these anisotropic crystal mechanical calculations. On the solver side, there are different ways of using it. We have, you can couple it to Abacus or to Mark-Mentat, which of course have the same kernel, essentially, just two different companies. We have also own solvers, so we mostly work with fast Fourier, with spectral solvers, because they are much more efficient than fine element solvers, of course. But you have different ways how you have to treat your boundary conditions. And we also develop an own 3D fine element solver. But you can couple it also, for instance, we have industry projects where DAMASK is also coupled to boundary conditions that you get from LS-DYNA. For instance, when you do process simulations, companies use typically LS-DYNA.
Okay. Can it go down to the atomistic scale? Is there any atomistic approach incorporated? No.
No.
Okay.
No. That is really the constitutive formulations are
continuum based. Yeah.
Exactly. They are all mean field and coupled to the continuum equation, continuum kinematics. Okay. And so you only go down to dislocation populations, which are formed in type of rate theories and master theories, and that then communicate through the O1 equation, essentially through the components of the local strain tensor. But we of course work on other projects closely together with our colleagues department on the atomistic side, where we, for instance, can in a Jupyter workflow also combine getting certain data, of course, from density functional theory or from atomistics. Okay. But the DAMASK code itself is not an atomistic code, not like LUMS or something like this.
No, it is a continuum approach. Yeah. Okay.
Exactly. It's a continuum crystal mechanical approach, also with phase field. And for atomistics, you would rather use LUMS or DFT, VASP packages, and so on.
Okay.
Okay, sir. Next question from our YouTube live. Can we use this technique to determine local stress at grain boundaries?
Yes, that can be done very nicely, and we have done that intensely in the past. So what you cannot mimic is really an immediate pile-up situation, like you would do it in discrete dislocation calculations, but you get the local refinement from a mesh refinement before the grain boundary. You get a gradual increase of the dislocation population inside all of the elements or integration points, and that gives you also a detailed simulation access to strengthening at grain boundaries. But again, this does not go down to individual dislocations, but to mean field description of dislocation populations. But yes, this can be done, and we have done this a lot in the past.
Okay, sir. Sir, next question again from YouTube Live by Satyabrata Dhala. Serial section gives microstructural input like orientation, but how can you compare the simulation deformation results?
Yeah, so you get correctly said the topology and the dislocation content and so on. And when we when I understand the question correctly, you want, for instance, to measure the local strain, for instance, also in 3D. then you would have to retrieve to so-called cross-correlation EBSD techniques. The cross-correlation EBSD technique is a technique that is different from the classical EBSD, where you analyze and invert the information from Kikuchi or pseudo-Kikuchi diffraction. But cross-correlation EBSD, you take all the polar points from all intersections, from all Kikuchi lines, and the relative shift of the polar points from a total Kikuchi map gives you then an access to the inversion of the local strain field. That means you can nowadays make local strain measurements with so-called cross-correlation EBSD. And there are 2 or 3 different techniques where we also intensely work on the further development. So this is now the gold standard on a microscopic strain measurement.
Okay, sir, thank you. Sir, next question by Amit Singh. Sir, can we use this to address the scattered flow behavior of trip and twip kind of steel?
Yes, the development of constitutive laws for TWIP and for trip mechanisms was one of the main activities of the past 10 years. And I could touch upon this only very briefly, but we have a couple of papers. I would be happy to share that with you, how it is implemented in DAMASK. In principle, we stay on the constitutive side that you know from Cox-Mecking type and Orban type of mean field theories. But now you couple it, for instance, with the theories of Subhash Majan, where you describe out of the dislocation flux and the dislocation population, the nucleation events you need, for instance, for a TWIP event or for a TRIP event. So you couple the dislocation information to have an information about the nucleation rates of TWIP and TRIP. And the kinematics of the martensite, for instance, of the epsilon martensite, of twins is then very similar treated like dislocation slip systems. So you have shear planes and progression vectors. So similar kinematics, but of course just more degrees of freedom. And the strain hardening works like I showed you before in mean field modeling, that you reduce by the enhancing interface density that you get both from TRIP and TWIP. You reduce the harmonic mean free path for the dislocation, thereby in a mean field theory describe the strain hardening. And we have published this in a couple of papers to show how you blend this TRIP or TWIP response into constitutive dislocation laws. And they are fully implemented in DAMASK.
Okay, sir. Any question from Microsoft team? If you have any question, then you can unmute and ask. Participant from MS team?
One question.
Yes. Yes. First question by Sumit Kumar.
Yeah, I just wanted to check, like in these simulations, in real world, you also have some surface roughness effects, like in rolling or especially in close pack rolling, where you have 2 sheets, especially in foil rolling. In those cases, can it simulate the surface roughness effects also? And the other question is, how does it, correlate with the actual test, say erection cupping test? So how much does it match with that?
Yeah. So first question. So you can yes, DAMASK can be, or this crystal mechanical simulation methods can be used to simulate surface roughness, and we have done that in a number of industry projects over the past decades, mainly related to 6,000 and 5,000 aluminum alloys that are used for, outer skin parts of cars, where the surface roughness evolution is, of course, very important, as you know, like from bridging and roping, for instance, in 6,000 series alloys. So yes, that can be done, and that scales, by the way, very much with a cube texture volume fraction. Now, foil rolling, that was your second question related to foil rolling. When you are referring to aluminum foil rolling, we of course know this is a very, very, very complicated process. When this is what you meant, because this is essentially a hydrodynamic forming operation, as you know. So where you first need to have a viscodynamic model of what the liquid is really doing in the roll gap and what the real local constraints on the foil are. That's point number one. Point number two is that in many foil rolling operations, you have stacked foils. That means you have a very complex setting where you maybe roll up to 3 or sometimes even 6 foils together through that rolling gap, and we talk a thickness of only 1 micrometer often under hydrodynamic boundary constraints. So I'm just trying to convey that foil rolling is maybe about one of the most complex operations to mimic by crystal plasticity. In principle, you also know that when you have a 1000 series foil rolling product, you only have more or less one very long pancake-shaped grain across the thickness of the foil. And again, that would mean that, of course, crystal plasticity is capable of describing that. That's actually a real strength of crystal plasticity doing that. But the real problem in foil rolling of getting roughness and particularly the damaging out and so on is a proper understanding of the forming operation in the hydrodynamic limit. But yes, in principle, anisotropy can be captured by such models, but the art lies in a good understanding and coupling with elastina and the lubrication situation in the roll gap. That is the real challenge, I think. And Ericsson, the third question was the Ericsson test, when I understood it correctly. Yes, when you do a deep drawing test, Marciniak test, Ericsson test, this whole apparatus that forming people in the automotive or forming industry must, of course, do and go through. That, of course, is something we do very intensely and systematically with big companies. And that, of course, can be done very nicely with DAMASK, typically on the basis of local homogenization, on-the-fly crystal anisotropy with elastina or abacus, or on-the-fly calculation of yield surface parameter and so on. The entire apparatus of all scales of individual anisotropy of crystals can be done in DAMASK. And that is routinely done by many companies, including Mercedes-Benz and so on, where we have developed this like already 15 years ago. So that can be routinely done with DAMASK in conjunction with whatever abacus or mark or elastina.
Okay. Thank you, Professor. Any other question from MS team? One question from YouTube Live, which is what is the physics behind fracture or damage used in this simulation, and what parameters are used for validating this result?
Yeah, that is a good question, and I only had time to mention this very briefly at the end. So how we do it in DAMASK, how we currently develop this is in principle like what you know from the classical Griffith criterion from your textbook. When you remember in classical Griffith crack mechanics, you balance the elastically stored volume energy when you load a body against the free surface energy that you have to provide when a crack opens. And when you add to this the local anisotropic plastic energy, then you can put these three contributions, the elastic energy, the plastic energy, and the surface energy into a Landau functional, where you essentially subject it then to an integration point in competition to elastic, plastic, or phase transformation dynamics. That means when you have now, where you had before just only to solve the elastoplastic deformation at an integration point, this integration point can also decide whether instead it could go with a smaller energy consumption by not doing elastoplasticity locally or phase transformation, but instead open up a crack, when the Landau functional would say you save energy by opening a crack rather than deforming or transforming the point. So that is how you must think. Basic physical background is what you in principle know from a Griffith crack. Just cast into a nonlinear form, a plastic form, and cast into a classical generalized Landau form. So when you're interested, I could send you 2 publications where we have explained how you do that. But the crack is then in competition with the elastoplastic and phase transformation at an integration point. And the energy defines what's happening.
Okay, sir. Thank you. We will circulate your yes, sir, publications. Sir, if any question from MS team, otherwise I will take last question from YouTube live. Any question from MS team? Okay, sir, last question from YouTube live. It is, sir, if TWIF and TRIF is happening simultaneously, then how we can check which mode of deformation is dominating? Kindly assume materials is having both TRIP and TWIF effect.
Yeah, that's a very good question indeed. We know several materials where this can happen together at the same working point, if you want, or loading stage. By the way, not only in steels, but also in certain metastable titanium alloys. And in continuum theory, where you have a certain discretization of volume and a certain mean field description of these transformation and plasticity events, we always have to indeed associate a certain transformation event with a certain subvolume. So there are different ways of doing that, and that was already discussed long ago in continuum models like by Surya Kalidindi or so on, when he started to work on twinning problems in constitutive models. And we followed essentially in similar ways. So there are different ways of doing that. When you are at a very coarse scale, then you only can balance depending on the activation fraction of the two, a certain volume fraction trip, plasticity, or TWIP. And that is then homogenized at one integration point in a linear or quadratic or similar type of RVE model. So there are different representative volume models that mix the transformed volumes at one integration point when you think of a macroscopic description. So there's an RVE method, a mixing method in between. When you are very fine in your resolution, like I showed at the very end, where you can do something like a more microteuxture-based simulation, then you can, of course, have your local transformation event also individually at a certain integration point without interfering with another point that undergoes a martensite deformation. The third refinement method is one that we use in magnesium, where we, of course, do not have trip, but we have, of course, twinning events massively. And here we do it even refined, that we use phase field theory, where you really track the real growth of a twin by a phase field. But this is, of course, a very time-consuming way of doing it and not suited for homogenization. So there are different ways how you can do this in DAMASK with different levels of homogenization.
Okay, sir. Thank you. Robin, continue.
Thank you. Thank you so much, sir, for your outstanding presentation and clearing all the doubts of the attendees. It was a delightful learning experience for all of us, and to discover something new about this domain of computational materials modeling. I hope all the participants will be benefited from the knowledge you shared with us. Now, I would request Ms. Malavika Vissas, the Vice Chairperson of IIM Students Chapter NIT Durgapur, to present the vote of thanks.
I am audible to all. I, on behalf of IIM Chapter NIT Durgapur, would like to extend my heartiest gratitude to Dierk Raabe. Thank you so much, sir, for your talk today, and thank you for all the motivation, enlightening, so knowledgeable.
Malavika, sorry to interrupt you. Can you make your volume, increase your volume, that audio volume? I think it is very low. Please increase the volume. If that is the problem, yeah.
Am I audible, sir?
Yeah, now it's fine.
I, on behalf of IIM Students Chapter NIT Durgapur, would like to extend my heartiest gratitude to Dr. Dierk Raabe. Thank you so much, sir, for your talk today. And thank you for all the motivation and enlightening us with your knowledgeable and inspiring words. We hope to have many more interactions with you in future too. I would also like to thank all the members of the organizing committee for making the arrangements. Our faculty advisor, Dr. Arup Kumar Mondol, and Dr. Madan Mohan Ghosh, HOD, MMS Department, for their continued support. Last but not the least, a big thank you to to all our guest attendees and my fellow classmates for being a part of this event. Thank you. Thank you all.
So, Professor Raabe, thank you very much from my side and for accepting my invitation. And I'll be happy to invite you on other occasions later. Maybe through virtual mode initially, then once that things becomes normal, to the actual physical mode, we can interact. We can invite you in future events, international conference we have a plan to organize. So we'll be happy to have you and your advices always for the development, for the progress of the department we need from you. Thank you once again, Professor Raabe, for being with us, and we have enjoyed a lot your lecture. Thank you.
Thank you very much for having me.
Thank you,
It was
sir.
a pleasure to be there. Thank you very much.
Thank you.
Thank you. Bye-bye.
Bye-bye.
Bye-bye.